like to go over some of these toolpaths that we wrote for this particular job, and I'll kind of go down the list here. In fact, maybe the first thing I should do is kind of show what I did as preparation for the file. The first thing that I did was I came in here and I colored the slots a different color and the chamfers a different color, so that it would be easy to select these by the color criteria in the toolpaths. And we've got really easy ways of doing this. If I want to pick a face and I choose smooth edge, I can pick on one chamfer and it goes all the way around and picks all the chamfers, which saves a lot of time for picking. So I can literally go around here and make a couple of picks, and I can get all of these chamfers selected and change the color quite easily. So that quickly I got all the chamfers selected. And in the same way, we can also do it down here for these guys. I can pick a couple of picks and I get all these slots picked all the way around. So the file preparation time goes super fast. And the other thing that I did kind of along the same way was I wanted to cover up and put patches on here. So then what we do after we get the colors isolated, in order to make this easy, is I make some sets by color. So for instance, this chamfer is really just a set by color, and I've told it that this dark blue color belongs to a set or a level, and this green color is a set or a level. And so in that way I can turn everything off if I want, and then I can turn on just the chamfers and just the slots, and it's easily controlled by the color. So then I decided that I wanted to have some patches over the tops of these slots so that my finish tool can ride over the top of them without falling in. So what I wanted to do is make a composite curve that goes around this top side like that. Oops, let me back up and pick one spot. Well, actually, you know what? We got this neat tool called along open edge, and it forces the chain to stay along an open edge, and it's by display state. It has nothing to do with solids or what's open or closed. It's simply a display state along open edge. And so then if I pick the back side, it forces it to not make any wrong turns, which saves a lot of time, especially with big jobs when you're having to do a lot of chaining and you got to zoom out and zoom in and look for the wrong turns. So our composite curve is quite nice. Okay, so I got one on the outside, and then we're going to do one more on this inside. And then I can do just a faces blend between that outside curve and the inside curve, and I get a real nice covered surface. And of course I've already got these made. I just wanted to point out how easy it was to do it. Okay, so next so the first step then is that we create a clearance plane. Then we define a target part. Let me turn the stock off for a second. Alright, so the target part is basically just what we're going to take into the simulator in order to verify the tool paths against. And then we created the stock. And the way that I did the stock, yeah, I think I'll quickly show you that as well. Let me switch over here to the CAD side. This will only take a second anyhow. Of course this is already done, but I want to show you how quick and easy it is. Again, if I go into the composite curve, I've got a lot of nice options here. If I choose one by one, I can choose to skip over areas. So I'm jumping over this feature and I'm just running along the outside of the part. And I'm jumping over this, jumping over that one. Okay, and then I can create a bounded face based on that. Alright, and we're going to say OK. We're going to lift this up. Let's see, edit, move, geometry, linear. Alright, so this is just a stock representation, and you can see it's not perfect, but I've lifted it up 300 thousandths, and I'm safe everywhere except for one little spot here. So I go 400, and of course when you guys start machining this, I'm assuming that this shape isn't perfect, but we're actually going to be machining that on there. And all I'm really trying to do is just create the lower edge so that when we do the machining, I want the machining to stop relative to the shape of this and not be waterfalling real deep. So I'm not trying to make this perfect. I just want a fairly close representation of the starting point. So let's lift this up another 1/4 of an inch to be safe. And then say OK. And then I'm going to take this face that I made and go to the top view. And I'm taking this shape. And let's delete this line. And we'll draw a new line down here. And a new line, let's say about there. And delete these ones. And then I'm going to use the corner tool to patch this up. And so we can take any face and we can project it down to a flat plane and change the boundaries by just changing them in the sketcher. So here's the face and here's the boundaries projected down flat. So I've quickly modified that geometry to be what I'm guessing is the right size of starting point for the billet that you're going to machine. And I could be way off, but this is just what I expected was going to be the case. So now from here I can use a solid shell command, and I can give thickness to this, and let's see what this looks like. So that's at 1.25 inches. Looks like we want to go maybe 1.5 inches. Alright, anyways, again, I've already done this, but I just wanted to point out how I did it. So this is how I defined the stock, and this is really important. In Cimatron, when we define the stock, we're telling the software that this is what's sitting up on the mill, and this is what has to be machined. So we're always chasing the stock down to the part, and it makes it to be really efficient so that we're not wasting a lot of time cutting air. If the software knows where the stock begins and where the part starts, it's going to give you very efficient pass between the two. Alright, so let me just delete this stuff and kind of back up from where we were. And I did create a safety net here too, which also was real easy. I just did a chain and a sweep out from each edge. While our roughing always is chasing the stock, the finishers work a bit differently, and so it's nice to have this little safety net to catch, so that I'm never going to machine below this edge. And it's not really required. It's just kind of a good habit that I have to ensure that none of the tools go below this edge. So it's kind of like using a boundary, I guess, but I don't really like using boundaries. In fact, I hardly ever use boundaries in Cimatron. Alright, so let's go back to the NC side here and look at some of the tool paths. So I showed what we did with the target part and how I created the stock. And next, let's look at the first rough spiral pass. So I started with the 2-inch cutter, and we'll probably go through and show this in the machine simulator. But one thing is for sure, it's not cutting any air. It's starting right where we told the software the stock begins, and you can see that it's taking into account the shape of the stock model. And even my lifts here are all optimized. When the tool lifts up to go from point A to point B, it lifts up just enough to clear the other surfaces and the stock. Alright, then after I did the roughing with the the 2-inch bull cutter, I then decided to go over the tops with an 1.25-inch button cutter. And this is a cutter that I've used a lot in the past that I've been real pleased with. And I don't know whether you guys are machining this top face with a ball tool or a bull tool, but I just kind of machined it the way that I thought made a lot of sense. And let me just go to the navigator here and we'll run this for a second. So this is like our wireframe simulator, where we can actually show the tool running right within the Cimatron environment. But of course we also have the machine simulator, which we'll go into later. But this is what I thought made sense to machine this big face. This 1.25-inch button cutter was one that I used in the past, and it really did a nice job in a situation like this, because this tool likes ramping. It likes 3D machining, and this particular tool had a 236 radius, 1.25-inch diameter, and was made by Ramstar over in Canada, and we use a lot of these. The inserts are real cheap too, which was nice. So nothing real fancy here, just a parallel cut running across there. And of course with a bull cutter you can take a much bigger step over, right? So assuming this would be leaving a pretty small scallop for the shape of the tool and the size of the step over. And I think the step over that I did was 1/8 of an inch. So after this tool runs, the software knows that this top has all been finished. So when I go back and do a roughing procedure with the 1-inch bull cutter, it knows that the top has already been machined, and so now it's just chasing the stock along this edge. So now it knows that there's material along the outside of this part, and it's going after it. And you can see how efficient these paths are. And I also want to point out, you'll notice that it didn't recut this floor here, because up here the 2-inch bull, I was leaving 35 thousandths on the walls and only 15 on the floors. And then when I told it to do the 1-inch bowl cutter, I said I want to leave 30 thousandths on the walls and the floors. So it's chasing the 5 thousandths that it saw on the walls plus the difference in the radius of the cutters. But I'm further away from the floors here than I was there, and because of that it's staying away from this floor. But if I said I wanted to leave, say, 20 thousandths overall here, then it would have recut that floor, or sorry, not 20. If I had said 10, it would have tried pulling that last 5 thousandths off here. Or up here I could have said, 35 and 20, and down here I could have said 20 and 10. So depending on if it sees stock, it's going to chase it. So you can play with the numbers to get the exact kind of tool path that you're after. Alright, next, I understand that this floor here isn't flat, but you guys are okay with machining it flat. And so, for instance, when I measure from this corner over to this corner, we can see that there's a difference in the Z. Oops, hold on. From here, yeah, in fact, from here to there, there's a 6 thousandths difference in the floor. So the point is that this floor is not flat, but my understanding is that you guys would like to machine it flat nevertheless. So what we can do here with the 2-axis procedures, I can chain around this floor, and the software doesn't care that it's not flat. It's still a chain, it's still a 2D, but it's perfectly fine to chain a non-planar chain and then cut it with a 2D, which is actually quite nice in this situation. So I just chain around there, even though it's not flat. I can then go to the tool trajectory, and I just pick the Z bottom, and I can pick any point that I want, and that value goes into this parameter, and then save and calculate. And this particular path, I wanted it to work in a certain way. You can see that we're starting on the outside of the part and we're working in. I don't like plunging on floors, so this starts on the outside real nice, and I was even able to put nice rounded corners on it. So it's a really nice 2D path generated off of non-planar 2D geometry. Alright, then let's see, next is what does this one do? Let's go to the navigator. Yes, this one's going around the outside, and this actually was quite easy. I was surprised how fast it went. All we do is we chain around this lower edge of the part, and we call that the drive curve, and then we pick all the outside faces and we say stay 90 degrees to it, and it runs around there real nice, following this lower edge, staying tangent to the walls. I mean, this 5-axis procedure literally took about a minute or two to write. It was just nothing to it. And you can see it's staying square to that wall. It was a piece of cake. And if we wanted to do multiple passes there, it'd be no problem either. We can say we want to take 2 roughing passes a certain distance away, and then we want to come back and take a finish pass of 10 thousandths or whatever. All that's real simple to do. Okay, next are the slots. I want to go into the navigator to show this one as well. And I'm going to hit play. And what I did with this one is it was also real simple. It's called morph between two curves. I picked this chain on the inside, this chain on the outside, and then I picked the face to stay normal too, which is the floor. And it does a great job of giving me one pass in between the two chains. And then I just said I wanted to do roughing, so I said there was 350 thousandths worth of stock in this slot, and I wanted to take it in 25,000 step downs, and I wanted to do ramping. So as it's coming around here, it's going to do ramping around this slot the entire time. And of course the tool is staying normal to the shape excuse me, the whole time. And this one was super easy to write too. I was surprised how fast it was. And here you can see that's the ramp between one lane to the next, and you can see we're just continually ramping down. There's no plunging. It's a continual ramp the whole way around, which is pretty awesome. So we got this slot, this slot, this slot, and this slot, all done the same way. And then we got the chamfers. And I did take this in one pass. I debated back and forth about whether or not there'd be two passes, but it seemed like it was only about 1/8 of an inch, and I'm not sure what material this is. So I did take it in one pass. Let's go to the navigator. But again, with this, it was quite simple. Really, all it is I chain this lower edge of the chamfer, and then I pick the drive surface, which is the chamfer, and tell it to position the tool tangent to it, and it runs around there, putting the chamfer on, no problem. I believe that's a 1/2 inch, excuse me, a 1/2 inch tool with a 45-degree chamfer. Alright, so that's the chamfer tool that does all these all the way down to here, and then we get to the drilling, and this one's my favorite. This one, so if, we can just box pick all these holes that have to be done. The software puts them in intelligent groups over here and says, okay, you got 5 groups of holes that have to be done. And for instance, if I want to program these holes right here, I say define or modify a sequence. I pick the hole. It gives me just one of the holes, and it says, okay, how do you want to do this hole? Well, we're going to use a spot drill, then we're going to use a 265 drill, and we make the spot tool go 100 thousandths deep, and then we make the drill go all the way to the bottom at the full diameter, and I want to poke through by 100. And we see that the top is a variable represented by dp, the bottom is a variable represented by a, and so what I'm telling it is that the drill needs to poke through the bottom by 100 thousandths, and I don't know where a is, and I don't care. Once I program this one hole, it goes and does the whole group with these parameters, and it doesn't matter if this hole gets shorter or longer or is at different heights on the part. As long as the geometry is the same and we've told it to do so, it's going to drill all these holes 100 thousandths past the bottom. Alright, so I program one of these outside holes and it gets all of them, and I didn't have to pick all the holes. I didn't have to go and pick the points. I didn't have to tell it where the holes were. I program one hole and they all get programmed. It's just amazing. Then over here, let's see, I got this. Alright, I've got an insert being shown here that's going to be in my way. Give me a second. Fix that. I had these guys hidden earlier. For some reason they came back. Okay. Alright, so here what I've got is I've got a small hole that I did first, and I did this one spot drill, and then 188 drill. Okay, and then now that I've got that hole there, I wanted to do a helical boring for this guy. So when I defined this one, I told it that I'm using a 1/2 inch cutter and that I just want to do pocketing, and I want to do ramping. So I do a helical motion the whole way down. And then there was only a couple more groups. Let's see, we had this one. This one was spot drill, and then 406 drill down, poking through. And what's unique about our feature recognition is that we set ranges. So what we tell it up here is that from now on, whenever you encounter a hole that's 406, and maybe we want to make it a range of 405 to 407, because maybe some designers might fluctuate. You know, the best example for me is a 1/2 inch tap. You might get one designer that draws the tap drill diameter at 421, and another designer that draws a tap drill diameter at 422, when in actuality the tap drill diameter for a 1/2 inch tap is 0.4219. So it's nice to have the fluctuation of being able to set a range here. And so from now on, whenever it sees a range of 0.407 to 0.405, it'll say we're going to use a 406 drill on this range of geometry. So setting up the range is really what makes this powerful, because it doesn't miss things based on different designers' standards. And the same thing with the depth. Okay, so we got a sequence built for a 406 diameter hole, but what if the hole, what if the plate comes in a 1/2 inch thick, 1 inch thick, 2 inches thick? We want to have an acceptable range here for the height as well. So we might say that, well, from any hole that's a 1/2 inch in height all the way up to 3 inches in height, let's use this sequence. But if it's more than 3 inches, probably you're going to change the sequence to have a short drill and a long drill. So then your next sequence could be from 3 inches to 6 inches. You're going to use this strategy in order to accomplish these holes. So again, I mean, in literally just a couple minutes, I got all of these holes all programmed, and that was programming them the hard way from scratch. Once you program these holes and you save the sequences, the software will look at the geometry, it'll search the ranges, and it will attach the sequences automatically. So the next time that I drill these holes, it won't take a couple minutes, it'll take a couple seconds. It's quite amazing how nice it works. Alright, so that's basically it. I did want to show the machine simulator. Okay, so here we have the part in the machine simulator, and let's hit play. So this would be the 2-inch tool that's doing the roughing. And down here at the bottom we can actually kind of like fast forward through this tool. you see at the bottom of the screen, I'm sliding the toolbar down to the next tool, then I hit play, and it verifies all those moves to make sure that there's no gouging taking place. Then I'm going to hit play again. And this will be the 1¼ inch button that's doing the riding up and down the face of the part. And let's fast forward that one. And then, excuse me, let's play the next tool. So this would be the 1-inch cutter that's going around finishing up the outside of the part. And here comes the 2-axis procedure. And here's the ramping down in the slots. And we can turn the stock model off too. If I say hide the stock, and let's make the workpiece solid. Let's slow this down so we can actually watch the tool. And actually, also, this particular machine simulator is kind of a generic one. We do have real machine simulators that would actually have the part standing in, or the part would be moved as the machine table moves, and the tool would be stationary, and you could have a tool perspective where you're just like you'd be standing in front of the spindle watching the table move around. If we have a machine configuration, we can also view it in that way. And you can see the tip of the tool there. Yeah, you can see that I've mistakenly defined that insert as something to be violated, so it's telling me that I've got a collision against my tool and that insert. So that's the machine simulator, and like I said, it's pretty cool if you have the configuration files built in where you're actually looking at the tool and the table is moving in the same way that it would be on the machine. It's pretty neat. Thanks for watching.